to make it now. Okay, so we're going to finish talking just a couple things about Saturn and Jupiter, and then go on to Uranus and Neptune, and hopefully end up with some planets. So I thought that I had removed this slide. That's not a good thing because I didn't mean to have it here. This is the slide I meant to start with. Okay, so we're good. I don't think that we went through this summary slide about Jupiter and Saturn. Now, there are a few more on Jupiter and Saturn's weather because it leads us into the next two. But interesting things, no, we did talk about this because I talked about, missed part of them. Talked about the differences in densities.
Why are you measuring the density of units?
Because it's convenient. We usually measure the density in units of grams per centimeter cubed. And that's the same as a kilogram. Oh man, my handwriting. That's the same as a, well, it's not the same as it's the same as a gram per milliliter. And thus it's the same as a kilogram per liter. So that's why they have those units there. Because we're most comfortable using the unit where the density of water is 1. Is that Tiani?
No, but I'm just asking.
Just for the record, we're all expecting you to pay attention in class. But if you somehow get an alert that says Manchester City scored, you can share that. He won't. If he gets something that says Barcelona scored, he'll share that though. Okay. Neither of them have a surface really that you can define. It just gets thicker and thicker and thicker. And so what we see as the surface is just where the gas gets thick enough for us to start seeing it. And you go inside and you'll get to what we believe is probably a molten rocky core. Last class period I was asked, what's that molten rocky core like? And the real answer is we don't know. We can guarantee it doesn't look like you're on the surface of the Earth there because it's really high temperature and pressure. But it has some kind of solid core, they believe, that you should have a percentage of the elements that are the heavier elements that would sink to the center and form that solid. Both of them generate more heat than they receive. In fact, we learned all of the giants generate more heat than they receive. Where's that heat coming from? It's from the compression. We call it the heat of formation from them just being compressed. And so that's what it says here, heat of formation. Okay, so our first clicker question of the day. What is a belt on Jupiter? And there are two, oh goodness, I said give both correct answers, but I did not give you the option of answering 2 answers. So just choose one of the correct answers and we'll see how it lies. Sorry about the missed wording. Actually, it's not the missed wording, it's the missed setup, but got to record some scores. I'm getting down. Okay, Latifah and Jessica. Boom, we're all in. 3, 7, 1, 1. Okay, so Gabby, tell us what you think.
Well, I answered B, and I also would have answered D.
Okay, so you would have said B and D.
Yeah, and I remember that it was B because those are the smaller ones, and it wouldn't make sense for a belt to be one of the large parts of Jupiter.
Okay.
And then it's depressed. We talked about how, if you had a belt on, then it would be a smaller radius than everything else.
And she is correct. Now, of course, it's not nice to talk about somebody's portly size, but I use that as a description because it helps you to remember, right? So that you remembered it means it's beneficial to use it. And really, I'm not very ashamed. I don't have shame in the right places. So, good answers. Winds. Saturn and Jupiter both have winds. And those winds are winds unlike we see on Earth. The harshest winds we see on Earth might be somewhere around I think that during a tornado, you can get up to somewhere just above 200 miles an hour, which would be somewhere in the ballpark of 300 kilometers per hour. The highest wind speeds ever measured on Jupiter, 500 kilometers per hour. So significantly faster than the highest wind speeds on Earth. Of course, it's not scaling with size because Jupiter's much, much bigger, approximately 11 times the size of the Earth. But it is bigger speeds. And it's caused by something very interesting. It's caused by the Coriolis effect. Now on Earth, we have general patterns where it's hot at the equator, cold at the poles. And so the hot air at the equator rises, goes north and south, and because of the Coriolis effect, it creates winds that curve to go toward the east. So we have prevailing winds in the upper atmosphere that are going toward the east because the hot air comes up and then goes north and south because of the Coriolis effect. Because it's cold at the equator, the winds have certain directions they go. On Jupiter and Saturn, you don't have different temperatures, and so you don't have the north to south kinds of flows generally caused. But you do have storms that make hotter and colder regions, and so hot air comes up and then expands outward in both directions. There we go. And then the Coriolis effect causes the winds to go opposite directions after it comes up and starts spreading out. But those Coriolis effects occur more than they occur on Earth because we don't have the general hot to cold. And so what we have is storm fronts that are created on Jupiter and Saturn that are essentially circling the entire planet. We have winds, and you see we have wind speeds that alternate directions. So you have winds going opposite directions and causing real strong wind shears where the two meet. And so you see the belts and the zones, you typically have just a opposite direction for the wind in one versus the other. And it's caused by hot air rising and then going out. And of course, we're looking down from the top, so we're only seeing what's going on in the high atmosphere, not what's going down below. So this picture down here actually shows measurements. The black line is the most recent and best from the Cassini mission of the wind speeds as you go from pole to pole on Jupiter. I believe this is Jupiter, Cassini, yeah. And so you can see the wind speeds. Let me put a mark here for where 0 is. Whoops. That's not what I meant to mark. There's 0. So you can see that now in this picture, they're mostly going one direction, right? There's a lot more that's in the upper portion, a lot more up here than there is down here. But you have those alternating winds. And of course, if one is here and then right next to it you have here, that's a really big difference in wind speed. So you have these interesting patterns that are the result of it not having really a hot equator and a cold pole, but uniform temperatures throughout, so they're going around. Of course, what's going to happen where you have the winds going opposite directions? If winds go like this, what's it going to tend to make? We could do this physically. I could have like Max stand up and I'll pass him going one direction and Russell pass him going the other direction. We'll both rub him. What would he do? He would spin. And that's what happens at the places where they meet. And so you can see here a feature. This here is called the Great Red Spot. And then we have smaller ones here, 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 here. Here. All of those are cyclonic storms, spinning storms caused because of these high wind speeds. So here's a better picture of that Great Red Spot. And that Great Red Spot has been in existence as long as we've been observing Jupiter with telescopes. So we don't know how long it's going to last, but we know that that's one cyclone that's been going on for more than 300 years. Now, is it changing? Absolutely. We have observed through our time of observing these storms that some of these storms will appear where there wasn't a storm, so new storms can be made. Storms can join together to make a bigger storm. Storms have joined in with that great red spot. So these storms are transitory, they're not permanent. Nobody knows what may have caused this one to form in the first place. Maybe it's just a natural, storm started, got bigger, more storms joined in, got bigger and bigger. Or maybe it was, some catastrophic event, like a really big asteroid plunged in, and that's what started the whole thing, right? We don't know. But we know that it's been there a very long time. And the elevation goes up. It's 50 kilometers above the surrounding clouds. 50 kilometers is really tall, right? So it's a very significant feature there on the surface. And that's where you have the high wind speeds. Notice here, Galileo saw it. That's the first person to do any observing of the sky with a telescope. Well, for systematic scientific purposes. Saturn also has belt zone circulation patterns. It also has cyclonic storms. Everything's pretty much the same, but it's harder for us to see it with Saturn. With Saturn, we have the storms are deeper in the atmosphere, and so we don't see them as much, but they're there. And Saturn actually has higher wind speeds than Jupiter. It's smaller than Jupiter, but it has higher wind speeds. And that brings us to clicker question number 2. Which statement is true about winds on Jupiter and Saturn? All right. We had 0, 0, 1, 2, and 9. All righty. This one goes to Daniel.
Well, you just stated that.
I did just state it. That's right.
Wind speeds on Saturn are faster than Jupiter, therefore they have a higher wind.
That's right. I just said it. That's, I hope for 100% there when I just say something. I appreciate that you recognize, well, you did just give us the answer there. So we have high winds on both. What was the highest speed recorded on Jupiter? Roughly 500 kilometers per hour. And Saturn, I didn't give you a number, but even faster. Magnetic fields. This is the last slide, I believe, on Jupiter and Saturn. It leads us straight into talking about Uranus and Neptune. So Jupiter and Saturn, you have very strong magnetic fields. Now it says Jupiter's is 20,000 times stronger than the Earth's. 20,000 times. That's really, really strong. How do we, what things, there's multiple things we observe about the Earth's magnetic field. So name one, Russell. What's something we observe about the Earth's magnetic field?
The southern lights.
Okay, he hit the one I was looking for in the first shot, so I won't go to anyone else. Our northern and southern lights, the aurora borealis for northern, aurora australis for southern, those are something that occurs because of the Earth's magnetic field. The Earth's magnetic field redirects charged particles from the sun so that they don't come close to us here at the equator, or in regions close to the equator. We're not at the equator. But they're going to enter the Earth's atmosphere closer to the poles. And when those charged particles enter the Earth's atmosphere, they then interact with gases in the atmosphere, exciting electrons. They de-excite, they give off the light we see as the northern and southern lights. So, since we have those on Earth, if we have a really, really strong magnetic field on Jupiter, should we have northern and southern lights?
Yes.
Yeah, we should. Because it's still going to receive charged particles flying out from the sun, has a magnetic field that's going to direct those away from the equator and toward the poles. There is a difference, though, and you can see the northern and southern lights in both of these pictures. The auroras tend to be more in the ultraviolet spectrum because of higher energies involved. And so here you're seeing northern lights. That was a choice color to use. That's the same color. There's the color I meant to use. So you can see that they exist on both Jupiter and Saturn. Saturn's field is only about 500 times stronger than the Earth. That's still really strong. So both of them have really strong magnetic fields. The fact that they have magnetic fields tells us that there must be a conducting material going around in circles, and it must have convection. And as I said before, it should have a molten core that has iron in it in the center. Even though it's spinning, roughly 2 times faster than the Earth is spinning, you can't make that strong of a magnetic field if it was just in that core. And so that's where science said it has to be something else. And so they believe it comes from liquid metallic hydrogen that's farther out in the planet. Now looking at Uranus and Neptune. Now I looked for some slides that I used to have on Uranus and Neptune. I couldn't find them and didn't put them in. Uranus and Neptune, they look very similar, right? But they're not exactly the same. Their colors are different because of just a very, very slight fractional difference in the amount of, I think it's methane in their atmospheres. But it's absorption of red light, and one has just a little more and absorbs a little more red light. And so we have a little less red that's being reflected, giving us the difference in colors. The discovery of these is interesting. The discovery of Uranus was actually, the first time it was observed and recorded, the person thought it was just some random object and didn't make anything of it. But then William and Herschel and his sister Caroline were studying the sky, and they found this, and they identified that's got the orbital properties of a planet. And so William and Caroline Herschel found it. Herschel wanted to call it. Say it louder for them. Okay. King George's star in English. But that was not allowed because even then they said it's got to be God. He's not a mythical God. He's not a mythical God, not a real God. And so that was disallowed. And so it got the name Uranus, which means is who? All I hear him say is, oh, yes, we got it in the sky. Okay.
Well, take it.
Okay. So it's named after a god, not named after anything Nazi or bad. And so in studying these, most everything that we know about the gas giants still applies. We have things like a cyclonic storm that you can see there on Neptune. So we have the cyclonic storms. They have belt zone weather patterns, but we don't see the belts and zones at all because of the atmosphere. So we can't see those. The magnetic fields is, of course, what this is focusing on. And the magnetic fields are really bizarre. If you look at those fields, now, first of all, Uranus is tipped over on its side. 90 degrees would be perfectly tipped over. So it's about 8 degrees past being perfectly flat with its orbit. We still treat it as if it's, like this going around the sun. So for half of its orbit, it takes 84 years to do an orbit. So half of that, one of the poles is essentially full-time sunlight. So if you were on that pole, the day would last 42 years. And then when you get past halfway, it's nighttime for another 42 years.
Yeah, it's not that. You just burn out.
It would be a long time to sleep at night. And I would not be productive in a 42-year day. Of course, if you're on the equator, only when I'm treating the camera there as the sun, only when you're right here would you have permanent noon, right? You come over here, or permanent, not noon, it'd be permanent twilight. Come over here and you'd have days and nights occurring with each rotation. So it's only at the poles that you would have that 42-year thing. But it's a really bizarre rotation. But then if you look at the magnetic field is even more bizarre. The magnetic field of Uranus is tilted roughly 60 degrees from its axis of rotation. I had to look it up just to make sure what they're measuring from. And that angle is the angle between this, so I'll just put that down here. That's the 59 degrees. So its magnetic field is not even close to aligned with its rotation. In Earth, is the Earth's magnetic field aligned with our rotation? That's a yes, no. You can venture a guess. Close, but not completely. It's about 11 degrees away from being aligned on Earth. Why 11 degrees? Well, we assume that it's just, you got stuff rotating around, fluid dynamics, things get twisted up, and that's what causes it. Well, here, roughly 60 degrees, that's crazy. Also note, does that bar magnet, they put a bar magnet in there because it behaves like it has a bar magnet. We call that magnetic dipole. Is that centered on the planet? No, it's not. This magnetic field isn't even centered on the planet. The Earth is pretty much centered on the planet. So scientists are faced with a very interesting observation. The whole scientific method. Got an observation, you got to come up with a hypothesis to explain it because you're curious and you want to know. And then, of course, you have to test it. So the hypothesis that scientists have come up with is that inside of both Uranus and Neptune, you don't have high enough temperatures and pressures to make liquid metallic hydrogen. So it must not be liquid metallic hydrogen that's making this to begin with. So they say, well, there should be a lot of water in there and a lot of other chemicals, ammonia and whatnot. And so it's probably making a salty water that's conductive. And so this magnetic field must be created by this salty conducting water swirling around in there. And then they theorize there's probably like ice cubes in there. And so those ice cubes are going to cause very random motions of the water. And that must be the reason that it's so highly inclined and offset. How do you test it?
To the computer.
Yeah, you test it with a computer simulation. I don't know if there's any other way. And so, you have to take that as weaker scientific knowledge because it's not even any direct observations of a star doing it. It's a computer simulation. This is what would happen according to what we understand of physics. So, those are really bizarre. So I've summarized here what we know about the magnetic fields for all of the planets. We've already looked carefully at the things above that line. Mars has remnants only. And then we have Earth with a magnetic field of about 0.5 Gauss. A Gauss is a unit pretty much used for the Earth's magnetic field to make it so it's a room temperature number, roughly speaking. Venus has no magnetic field, and Mercury has a very, very weak magnetic field.
Why didn't they just make it like 1,000?
One would not really be an option because what they did is they just said, let's take the standard unit of magnetic field, which is the Tesla, and let's multiply it by just an order of 10, so 10 raised to some power, to bring it up to a normal size unit. And so it's 10 to the 4th is what they multiply it by. And I would say, why not multiply it by 10 to the 5th so we have 5 instead of a half? Because I'm happy with using them 5 and half. But I didn't make such a decision. Okay, but going on with this, you see the magnetic fields for the gas giants are much stronger than the magnetic fields for the Earth. Now, as I was preparing, I was looking up information on Uranus specifically. And you see here it says Uranus has a magnetic field that's 47 times the strength of the Earth's magnetic field. That 47 times is measuring the strength if you're the same location. Of course, Uranus is much bigger than the Earth, so that's not measuring the surface strength. It's saying if you're at the same location with respect to the center. And so, in fact, if you are on the surface of Uranus, and remember, just like Jupiter and Saturn, there's no actual surface. It's just gas getting thicker and thicker. But if you were there at the region we call the surface, some places the magnetic field on Uranus is as strong as 3 to 4 times the surface magnetic field of the Earth. Other places it's actually as low as 1/3 what you would have on Earth, because it's really wacky. But the bottom line is, it's a much stronger magnetic field overall, more energy in that magnetic field. Neptune has 25 times Earth's magnetic field. Notice Neptune's is the craziest of all in terms of the positioning of that bar magnet. So, well, I hope you picked up all kinds of cool things there, because I thought it was totally cool. Now we're going on to moons. That's all I'm talking about for Uranus and Neptune here. So moons. How many moons does the Earth have? You all did this before taking the class. One, right?
20,000 satellites.
How many what?
20,000 satellites.
The satellites you're counting are not natural. When Galileo used his telescope to study Jupiter, he saw 4 moons. He saw these 4 dots. We talked about them earlier when we talked about the history of astronomy. And actually, interesting story. Like any good scientist, he wanted to make good money for doing his science and not have to actually do anything that would be work-like. He just wanted to do science-like things. So he tried to get a wealthy businessman to hire him as a house scientist. Basically, the idea is, you will be my patron. I will be working for you. Any prestige, any stuff that I learn in science will then be a reflection on you, and everybody will say, you have such a wise scientist in your household. And Medici, it was the Medici family. And he had, at least from what I read, 4 sons. And so Galileo said, I will name these 4 moons after your 4 sons so that your family will forever be famous. But no dice. Didn't get the job. Still had to do something to make money. Things that old scientists did to make money are sometimes kind of funny. Like Johannes Kepler, right? We talk about Johannes Kepler. I talked about how intelligent he was. He made money by writing horoscopes. Why? Well, he knew the astronomy really well. So he could say when this moon is in this constellation or whatever, he can come up with that stuff easy. And then what do you do after that point? You make stuff up. Well, that's not that hard either. And so he would make people's personal horoscopes to make some extra cash. So in observing these, the reason that Galileo realized these were moons was because they orbit so rapidly. The closest one takes about 2 days to do an entire orbit. And so, you come one night and you look at its position, you come the next night and you look at its position, and it's wildly different position. And the longest one is only about 17 days to do an orbit. So he's seen these dots move all over the place from night to night, and he said that's got to be planets going around it. It can't be something that just flew by and then another thing flew by and another thing. That wouldn't make sense. So we have these 4 moons that we call the Galilean moons, or here it says Galilean satellites. Satellite just means something that's going around, so moons are satellites. So here are those 4 Galilean moons. Starting from the one that's closest to the moon, to Jupiter, going out, you have Io, or if you go to Disneyland or Disney World, Captain EO, it's the same thing. Io there is different than all the rest. Isn't it volcanic? Yes, it is. It's volcanic not because of things like what makes the Earth volcanic. It basically, as we talked about before, is like hell. Because you basically have sulfur volcanoes, which can't be any fun. And it's caused because it's so close to Jupiter that it gets very deformed by gravity. And as Europa passes outside of it, that causes further deformation. So it's constantly being worse. It's like you take a wire and you go like this and it gets hot. That's what's happening to that planet. That's what's generating heat to make it volcanic. Question, Max?
How big are they compared to the Earth?
How big are these objects or the volcanoes?
The objects.
They're actually very small compared to the Earth. I'll show a picture in probably, I think it's the next slide. No, it's 2 slides from now. That shows the size of the moon compared to these other moons. So then we'll be able to make a good judgment. We do have the sizes here. For Io, it's around 3,600 kilometers in diameter, and the Earth is almost, 6,300 and some kilometers in radius. And so the Earth is about 4 times, roughly speaking, the diameter of Io, just to give you a ballpark. Okay, so we have the size, and of course, this is showing 3 dimensions on the size because it's not perfectly spherical, right? It's oblate because of the action of Jupiter's gravity and Europa passing by. Europa here is actually a little bit smaller than Ganymede. Is the largest of all of the moons in the solar system, 5,262 kilometers in diameter, or maybe 40% the size of the Earth. And then Callisto is just a little bit smaller. You have their masses over here. I'm not going to worry about that. The densities I will worry about, though. We've talked about the densities pretty significantly. And if you look at the density of Io, what does that tell you? You look at that number, what kind of density, what other objects have you seen with densities like that? Okay, Venus. The uncompressed densities of Venus and Earth are what? 4.2? The density and uncompressed density of Mars is like 3.3-ish. So that's in the ballpark of the densities of the Earth and Mars and Venus. So probably a composition that's similar in the types of stuff. So the composition, they don't have any water in that composition, but they do have a core, probably a metallic core, and then a mantle. Not a molten core. Why would you not have a melted core in Io? Its size is big or small?
Small.
Its size is small. And we learned that smaller things cool more rapidly because of the ratio of how much energy they contain to the surface area. And so something small like this should have cooled pretty rapidly. And so now any residual heat is just heat caused by the tidal forces. And so it shouldn't have a molten core, not something that's still melted from when it formed. So this is probably basically a rock. Now we look at Europa. Europa's is a little bit less than any of our rocky planets, definitely more than any of the gassy planets. It's more than Pluto. Pluto is somewhere around 2, which we interpret to say that Pluto is a mixture of ice and rock. And so we say this here, it's probably also a mixture of ice and rock, but a lot more rock than Pluto has. And so analysis of Europa says that you have a crust, and under that crust is an ice crust. And under that ice crust, you have a water ocean. And under that water ocean, then you should have a rocky core. And when scientists look at Europa here, they conclude that of all places in the solar system that aren't named Earth, that's the most likely place for life to be able to live. And so scientists are really keen on someday sending a probe here to Europa in search of life, because they believe that they could probably have life down here in the waters under the ice. Its energy source would be vents of, from geothermal vent, well, not geo, of course, not the Earth, but thermal vents coming up to heat it up. Going further down, we have Ganymede and Callisto. Ganymede, that looks a lot like Europa, just more water. Why do they speculate more water? Because its density is lower. Right? The calculations just follow the density. Question?
Do they think that there's there's a chance of life on Ganymede?
I believe so, yeah. But they believe Europa is probably the most likely. Question, Gabby? Yeah, okay. And then we have Callisto. Callisto, the artist's conception here doesn't look like the others. Don't believe Callisto has any liquid water anywhere. Everything's frozen. Has a frozen exterior. And if you look at the exteriors of these, you see lots of pockmarks, signs of collisions, right? So you have to have a fairly old surface to still have signs of lots of collisions because the frequency of collisions has dropped over time. So a young surface has very few craters. An old surface has lots. So you look there at Callisto and you say it must have had its surface frozen for a long time. If you look at Ganymede, Ganymede has a lot of craters, but it has big regions that have far fewer craters. And so those must be much younger regions where you've had liquid water on the surface and then it's frozen over again. So not frozen as long. Europa, instead of seeing impact craters, you see all of these lines. Those lines are believed to be the equivalent to faults on Earth. But this is in ice. So basically it has an ice shell instead of a dirt shell like Earth, but you still have essentially plate tectonics with these ice shells. So they will, be pushed together or pulled apart, broken and fractured. And so those lines you see are places where it's been broken and fractured and water comes up between and freezes, just like magma comes up between our rift valleys and freezes to make new ocean floor. So they believe that the surface there of Europa is fairly active. It's a young surface with plate tectonics, but water instead of rock. Very interesting conclusions they draw based on scientific knowledge and observations. Now, there's more to see here. The periods. Notice the numbers in parentheses. The period for Io, I'll just write Io over here, is 1.769 days for it to do an orbit. It's not even 2 days. And the period for Europa is 2 times that. The period for Ganymede is 4 times the period for Io. Now, if you think about that, what does that tell you? You have orbital resonances here, 1 to 2 to 4. Why would you have such an orbital resonance?
So you don't end up as a ring.
Because what?
So you don't end up as a ring.
So you don't end up as a ring? It's not so you don't end up. It's for the same reason that you have to worry about making them. It's the tidal pull. As one of the planets gets closer, it pulls. So as you overtake, you pull that one back, and then as you go past it, you pull it forward again. And if the moons are constantly interacting and exchanging energy to set up these synchronizations, because it's a lower energy situation if they have these resonances. Now, if we get out to the last one, if we go out to Callisto, I hope I remember them in the right order, it is not 4 times the preceding one. It's a little bit longer than that. Theory is, good, I was just checking to make sure I did remember the right order. Theory is that Callisto is slowing down and will continue to slow down until it comes into sequence. Because it's the farthest one out, it's got the least action from the others affecting it, and so it's the one that's taking the longest time to get locked in. But at some point, it's assumed, sometime in the very distant future, not our lifetimes, you'll have a 1, 2, 4, 8 resonance sequence going on, which is really cool, I think. Okay, enough of the Galilean moons. I got 10 minutes left. So all of the moons, how many total moons are in our solar system? I don't know. A very large number. We only have 3 moons in the terrestrial planets, 0, 0, 1, 2. It was thought that maybe there should be a sequence 0, 0, 1, 2, maybe 4, for Jupiter, and then keep going 1, 2, 4, 8, 16. Maybe it went like that. Now, there's no rhyme or reason to it. It just seems kind of random that it's 1 for us and 2 for Mars, especially if you consider the types of moons. Our moon is nothing like the moons of Mars. It's not like, oh, it was farther out, so it made 2 of them, because there's nothing like it. Jupiter's moons, here we can see the size. This is not the one I was referring to. There's a better picture of the next slide. But we can see the size. And of the moons here, there are only 1, 2, these together are another 4, and 1. Those are all the moons that are significant moons. Moons that are of a type like our moon. Or to put it another way, those are objects that if they were by themselves, could have potentially qualified as planets. Right? All the moons of Jupiter, if they were off by themselves, they would qualify as a planet. The Earth's moon, if it was off by itself, it would qualify as a planet. All the rest of them, not so. The rest really are going to be asteroids. And so most of the moons in the solar system are asteroids that have been captured. And it's just a small number that are actually big objects that are more interesting to look at. So of the ones that aren't labeled here in green, they have often irregular orbits. Some actually orbit backward. So you have moons that are going like this. It's kind of cool, right? How can that happen? It couldn't have happened from the traditional story of how we had a big solar nebula that collapsed and everything went around in a circle, because that should have everything going the same way. Now we hypothesized, theorized that it must have been a very major impact that made Venus spin backward. Well, these are moons. It's not an impact that would make the moon go around backward. It's simply, here's the object. If an asteroid comes in like in front here, it might end up going like that. But if it comes in behind, it might end up going like that. It's just the angle direction that the asteroid was coming on when it was captured that determines what direction it's going to orbit. Most end up orbiting the same direction as the planet is going around the sun. But it's not a given. It's possible to go the other direction. And these orbits can be eccentric, all kinds of fun things. But nearly all end up getting tidally locked. They end up getting tidally locked for the same reason the moon's tidally locked, the same reason that Mercury has its very obscure orbit. Because you end up with a lower energy situation, you tug and tug until it gets into this lower energy situation. So here's the picture I was specifically talking about. Here you can see the major moons. Triton, which is Neptune's moon, Neptune's major moon, and Titan, which is Saturn's major moon. And I get those two confused because they sound too similar. And then we have the 4 moons here of Jupiter, and we don't see the Earth's moon. I thought we did, but the Earth's moon is something like about someone like that size. It's close to, but not as big as Ganymede. So those are the major satellites. Those look like their own objects. Here is another satellite, Amalthea, which is 250 kilometers across. 250 kilometers compared to the Earth, that's minuscule. On the other hand, 250 kilometers is, about the distance from, I don't know, here to Sioux City or something like that. So it's a pretty big distance if you're driving. Not such a big distance if you were to put it into miles, it'd be something like 150 miles. I don't know how close things are around here, so. This picture you might have recognized was at the first slide. The surface temperatures of all of these Galilean moons, 110 to 130 kelvins. Is that hot or cold? Cold. We established that. Just want to repeat, that's a cold temperature. At that temperature, do you suppose ice is hard, soft? somewhere in between.
Probably harder than steel.
Yeah, probably harder than steel. So when I talked about like Europa having an active surface, that doesn't mean that it's soft ice that's easy to break. It's really hard ice because it's so cold. So, yeah. Does this have the Earth? Yeah, here's the Earth's moon in comparison to size. Well, no, it's not. Because Earth's moon is not smaller. I don't think it's smaller than Titan. Maybe it is.
Titan's pretty big.
Yeah. I thought that it was only Ganymede that was maybe bigger. So y'all got a picture of which one's the biggest here?
Looks like Titan. I think
Ganymede's the biggest. Because, clicker time. Which is the biggest? Good call.
So what do you mean?
To just keep flashing up Man City scores.
No. It says downloading content.
Really?
No idea.
Okay. All right. Well, we had 9 and 2. And if I were to ask anyone why they said Ganymede, it would be because I just said, no, Ganymede's the biggest and circled it before we went over. 2 people said Io. Io is not as big. Not as big. All right. Now looking specifically at these objects. So here's looking at the surface of Io. You can see on the limb a volcano. Volcanoes show up nicely on the limb means looking at essentially the horizon from a distance off. And so they show up nicely on the horizon. And if you look at the surface, you will have, here's a volcano. And the volcano eruption goes up and then just goes like flat. Kind of like Earth, maybe you've noticed that you will have a fire and the smoke goes up to a certain distance and then it heads off sideways because you've reached a temperature change where it can't rise anymore. And so that's basically what happens there. The ash just goes off and you end up getting these big trails where the ash falls down. So you have black streaks on the surface of the planet from those trails that go off of the volcanoes. And this just talks about the things I've already said. Sulfur spews up out of the surface. Hellfire and brimstone, friends. That's what it's like on the surface of Io. Europa, I talked about those cracks in the ice sheet. And so it's covered with cracks, young surface. The water is mineral rich. That's what gives it its pretty color. Probably iron, just like Mars is rusted from iron to give it the color. It does have heat from its interior that's probably enough to keep that ocean liquid, and it's that heat from the interior that they think makes it so you could potentially have life. So consider it a hot spot region for life. I'm surprised they didn't show a little vegetation growing down here, just to plant the idea. If you look at Callisto, now if you look at Callisto, you see these things right here. Those look like what I just showed you on Europa, right? So there is evidence that that's Ganymede, excuse me, not Callisto. Callisto's the lower one. The Ganymede used to have that kind of thing going on. And as I said, it has regions that look younger, but it has a pretty deep ocean covered by a surface that's ice with crater. Callisto is just frozen. It's solid, nothing going on. It probably just formed and froze and never even differentiated, just too cold out there. Then we get to Saturn's moon, and I guess we'll talk about Titan on Friday after the quiz.